Hello YouTube. Today we will be proving stuff about, well, null t and range t, so null space and range. So let's go. First things first, let's show that the null space of t is a vector space. So if x belongs to the null space, then x belongs to V due to the way how null t is defined. So null t is a subspace of our vector space V. So if we want to show that null t is a vector space, well, this is equivalent to showing in this case that null t is a subspace of V, which is equivalent to showing this. So let's just show this to show that null t is a vector space. So take two arbitrary x, y from null t and some scalar alpha, and let's see. So we have to show that this thingy belongs to null t, which is equivalent to showing that t maps this thingy to 0. So let's apply t to this sum over here, this linear combination of vectors. So we have that this is equal to this. Imagine here's an alpha. I'm too lazy to fix that now. So due to x and y belonging to null t, we have that t of x is equal to t of y, which is equal to the 0 vector. So we have that t of this linear combination is equal to this, which is equal to, well, 0 plus alpha times 0, which is equal to 0. So for all x and y belonging to the null space and for all scalars f, this thingy always belongs to null t, establishing that null t is a subspace of V, so it is a vector space. Done. Next, let's show that the range t is a vector space. So, very simple. Due to t being linear, its whole job is to take vector spaces and map them to and transform them into other vector spaces. So V is a vector space, t is linear, so this thingy over here, the range, is also a vector space. Now, let's talk about the following concepts we will introduce, give a definition for. So a bit of motivation. Here we have two sets, so 3 elements here, 3 elements here, and again the same arrangement here. We have some function f, which takes each of these thingies and maps them to something over here. And here we have q that also does the same thing, but in a different way. So these collections of arrows are the totality of f, and here we have q. So in figure 1, our function f is such that the number of elements in range of f, so so this is the range of f, is equal to the number of elements in X. So here are 3 of them, and mapping them, and we still have 3. Great. So we started with some number of elements, did something to them, F being that action, and we ended up with the same number of elements. So that's picture 1. Now in picture 2, q is such a mapping is a function such that the number of elements in range q is less than the number of elements in X. So we started with 3 over here, mapped them, we mapped them to these 2 points. So we have 3 over here, but the range only has these 2 points. So what caused it to lower the amount of stuff? Well, let x1 to xn be all different, so some points in X. So no xi is equal to xj, except, if I pick the same element twice, then xi is equal to xi. So apply f to these to get all of these, f of x1 all the way to f of xn. And now, if it lost some elements, well, if there exists, f of xi and f of xj, where I and j are different, so for example, this is f of x3 and this is f of x5, such that it turns out these two are equal, so this situation over here, this gets mapped here, and this gets mapped here, so you have your xi, xj, and you have that your f xi is equal to your f of xj. So that's the picture. Then, this list over here, these two are the same elements. And since for sets really don't care about repetition of elements, so this set over here with a bunch of x's is just equal to this set over here with just the one x. So we lose an element when we plug this list, this this stuff into the set, well, the set sees, oh, these two are the same, so it gets rid of one of them, so we just get this. So here we had n, and here we have n minus 1. So functions like the one in figure 1 we call injective, so these thingies over here. So the formal definition is some function f is injective, or one-to-one, if the following holds. So if you take two different elements from your x and you map them, well, then the images, the results of the mapping are different. And now also to introduce the concept of surjectivity. Now, onto mappings. God, I hate French. So in figure 1, range 1, so this x gets mapped to, well, y. So the range of f is equal to y. Whilst, you know, in picture 2, let's go back to picture 2, we have that, well, the range is like these 2 points. So we don't get this point. This point is in y, so the range is strictly, it's a proper subset of y. So here, range of q is a proper subset of y. So we say f is surjective onto, due to mapping x onto the whole of y. So if f is surjective onto, then it maps x onto the whole of our target set y. So formal definition, f function is surjective onto if the range of that function is equal to, well, the set it maps x to. So now let's show that. So let V and W be vector spaces and T some linear transformation between them. Let's show that T is injective. So this linear map T is injective if and only if null T, the null space of that transformation, is equal to, well, just the zero vector. So let's suppose that T is injective. Take some arbitrary element from null of T. Well, we know that the zero vector, when you apply t to it, it definitely gets mapped to the zero vector over here. That's just what linear transformations do. And this is also equal to t of v by the definition of v, because it belongs to null t. So we have this equality. And now by injectivity, so the formal statement of injectivity was that if you have two different elements, they get mapped to two different elements. This is equivalent. It's the same as saying that. So you got this implication and you can take the contraposition. So if this doesn't hold, then this doesn't hold, which is equivalent to saying that if two of your images are the same, then the two elements that got mapped to that are also the same. So you go in reverse, kinda. So that's an equivalent statement of this. So we will be using the other phrasing of injectivity. So we have this. From this, due to injectivity, it follows that v has to be equal to the zero vector. Thus, so we took an arbitrary v, and it turns out that v always has to be the zero vector, so null t can only contain the zero vector. Now let's suppose that null t is just this set. And we would like to show, well, injectivity. So take tv, tu belonging to range of t. And now assume, so set them equal to. And from this equality, our goal is to get, well, that v is equal to u. So we assume this, and this is just equivalent to this over here. Now, due to t being linear, we have that this is equal to this. So, thus, v minus u is a vector such that it gets mapped to the zero vector. So it belongs to null t, and null t only contains the zero vector, so v minus u has to be equal to the zero vector, i.e. v is equal to u. So we assume that this holds, and we got to here at establishing the injectivity of t. So null t encodes whether t is injective or not. And injectivity is a sort of number of elements preservation property. So us stumbling upon, the set null t, the concept of null t in the analysis of in the case of when the dimension of range t was less than the dimension of our starting set, if you recall. So this thingy popped up in this case. So yeah, should seem less surprising now, since we see that null t is directly encoding injectivity, and injectivity is about preserving the number of elements. So, if the dimension of this resulting space is less than the starting space, obviously some number of elements probably got lost or something. So cute. And now we get to the meat of today. So theorem. This is the Rank-Nullity Theorem. So if V is finite dimensional and T is a linear transformation from V to W, then the range of T is a finite dimensional subspace of W, and here it is in all its glory. This holds. The dimension of V is equal to the dimension of the null space plus the dimension of range T. So let's prove this. So T is a linear transformation, goes from V to W. Thus, the range of T is a subset of W. So range T is a vector space due to T being linear and due to W being a finite dimensional vector space. Range T is also finite dimensional with the dimension of range T is less than or equal to than the dimension of W, establishing that range T is a finite dimensional subspace of W. So we got rid of this statement over here. We got the job done there. Moving on. If V belongs to null T, then V belongs to V. So null T is a subset of V. Null T is a vector space. Thus, null T is a finite dimensional subspace of V due to V being finite dimensional. So we got null T is a vector space inside of a vector space V. V is finite dimensional, so null T also has to be finite dimensional. So the dimension of null T is less than or equal to the dimension of V. And now, since null T is a finite dimensional vector space subspace, there exists a basis for it. Some B of null T with the following vectors. So U1 all the way to UM. So there's M of them. Now, due to null T being a subspace of V, we can extend this basis B of null T to a basis of the whole space V. So we expand B null T to some B which contains, well, our original starting vectors, so U1 all the way to UM, and then we add some more vectors to it until we get a basis, so some Rm plus 1 all the way to Rn. So we have M of these, and this is the dimension of null T, and here we have, well, N minus M vectors. So this whole story establishes the following. The dimension of V, so the number of elements here, well, is equal to these over here, which are the dimension of null T, plus N minus M of these. Now, looks like the thing you were trying to prove. So we want to show that this N minus M is equal to the dimension of the range of T. So let's see if we can show that when we apply T on these vectors over here and get these vectors and put them in a list. Let's see if we can show that this is a basis of range T. For if we did that, we would be done with the proof. So if something wants to be a basis, it has to span the space. So first of all, let's see if this list spans the space of range T. Well, take some arbitrary TV from range T. By the definition, that means that there exists some V belonging to our space V such that V gets mapped to T of V. Now, due to V belonging to our finite dimensional vector space V, there exist scalars A1 to AN such that we can express V as the linear combination of, all of these vectors over here, the basis vectors. So here. Now apply T to this. So we get that T of V is equal to this. And now, due to u1 all the way to um belonging to null t, so they're the basis vectors of that space, so they also belong to that space, so they all get mapped to 0 by t. So we end up with just having that t of v is equal to this linear combination, establishing that indeed the span of these vectors is the whole of range t. Now, all that's left is linear independence. So, is this list of vectors linearly independent? So, the way we set up things, we have that V can be split up into two subspaces. So, we have our nullity subspace, which is generated by all the vectors u1 to um. So that's the basis of this space. And then the remaining vectors, you know, rm plus 1 all the way to rn, they give rise to this over here, which we'll call R. Now, if this list was linearly dependent, then that would mean that one of these vectors could be expressed as a linear combination of the others. We would do some algebraic manipulation, and we would end up with that there would have to exist some vector r belonging to our big R, which is different from 0, such that it gets mapped to 0. So that would mean that if I just look at the null space of my transformation t, when I just look at it, what it does to all the thingies in R, so I know that t already maps all of this to 0, this whole space, due to it being the null of t. But if this was the case, if these were linearly dependent, then null of t when restricted to R would have to be different from this vector. So there would exist some other non-zero vector in it. But all the possible v that are different from 0, such that t of v is equal to, well, the 0 vector in W, are contained within null t. That's the whole point of null t, for it to gather all of these vectors. So we would have that, due to all of this reasoning, null t of R would have to just be the 0 vector, because all the other vectors would be contained in null t, only leaving the 0 vector. So we have this, and simultaneously this. We got into a contradiction. What led us to the contradiction? This assumption that these vectors were linearly dependent. So we have established now that this cannot be the case. This assumption cannot hold. So a list is either linearly dependent or linearly independent. So this is not linearly dependent, so it has to be linearly independent. So we've established that this is linearly independent. And now combining everything we got, we have that the dimension of V is equal to n. So we go from 1 to n, so n vectors. And this can be written as m plus n minus m, so valid. And what is m equal to? Well, m is equal to the dimension of null t. What is n minus m equal to? Well, it's the dimension of range t. So we finally get that the dimension of V is equal to the dimension of null t plus the dimension of range t. So yeah, hope that made sense. Take your time, go over it, ponder it. That's what mathematics is all about. In the next video, we will be showing how linear transformations, what linear transformations have to do with like systems of linear equations. So yeah, look forward to that. Have a good one, and see you in the next one.